physicists discover transdimensional state of matter that defies 2D and 3D classifications. Physicists have identified a previously unknown quantum state of matter that exists in a unique middle ground, behaving as neither fully two-dimensional 2D nor three-dimensional 3D. This discovery, termed the Transdimensional Anomalous Hall Effect, TDAHE, challenges existing theories of how electrons move within materials and opens new avenues for understanding quantum mechanics at the nanoscale. The unexpected discovery, the breakthrough, came from research led by Lei Wang at Nanjing University in China. The team was investigating a thin carbon-based material, structured with atoms arranged in rhombus patterns, hoping to observe highly efficient electron currents. Standard physics dictates that when a thin material is placed in a magnetic field, electrons trace small circles and are pushed to the site of phenomenon known as the Hall effect. In magnetic materials, this choreography becomes more complex, leading to various versions of the effect. However, when the researchers applied two mutually perpendicular magnetic fields to their carbon sample, the electrons reacted in an unprecedented way. Instead of conforming to standard 2D or 3D behaviors, the electrons executed looping motions both horizontally and vertically. This was particularly puzzling because the material was only 2 to 5 nanometers thick, too thin to physically accommodate the vertical motion expected in a 3D space, yet too complex to be explained by simple 2D physics. TDAHE came about as a complete surprise, a phenomenon never seen in any other material before, nor does any theory predict that, says Wang. After we measured the raw data, we spent about 1 year trying to understand it. Initially, the team suspected experimental error. However, repeated tests and the creation of new samples consistently confirmed the results. The data proved that electrons in this specific thickness range were operating under a new set of physical rules. Defining a new regime, the term transdimensional does not imply that the material is a simple hybrid of 2D and 3D properties. Rather, it signifies a new regime that exists outside the well-studied categories of conventional dimensionality. Andrea Young, a physicist at the University of California, Santa Barbara, offers a deeper theoretical perspective. He notes that the defining feature of this state is not just its thickness, but the lack of symmetry in the mathematical representation of the electron states. This asymmetry manifests in 3 distinct ways, a novelty compared to similar known states. Young describes this new state as a type of quarter metal. In conventional metals, electrons have significant freedom of movement. In this transdimensional state, the lack of symmetry severely restricts what electrons can do, creating a unique electronic environment that has no direct parallel in standard 2D or 3D materials. Why this matters: this discovery highlights the complexity of quantum mechanics at the nanoscale. It suggests that our current models, which often treat materials as strictly 2D or 3D, may be missing critical intermediate states. Understanding these in-between regimes could lead to new electronic materials, developing components that utilize these unique electron constraints for more efficient or novel computing applications. Advanced sensors. Wang's team plans to use diamond-based magnetic field sensors to further probe this state, potentially leading to more precise measurement tools. Broader physical insights. Identifying transdimensional physics in other materials could reveal a wider class of phenomena that currently lie outside standard theoretical predictions. Conclusion: the identification of the Transdimensional Anomalous Hall effect marks a significant step forward in condensed matter physics. By revealing a state of matter that defies traditional dimensional classification, this research expands the map of quantum behavior and underscores how much remains to be discovered in the nanoscale world.